Chapter 6, Measurement Error. So to start with, we're going to ponder the question of, is an individual measurement an exact value? So for example, I might tell you that your calculator weighs 9 ounces or that John's height is 73 inches, but are those the exact values, the measurements that I'm telling you? So data is often made up of measurements, i.e. height, weight, length, but we found that if the same thing is measured several times, several different measurements are likely. So for example, when I measured my baby 5 times in a row on the same scale, I got the following measurements: 16.52, 16.65, 16.33, 16.21, and 16.45 pounds. My scale is not broken, it's just that we found that we can't measure as precisely as we might want. And so we've come up with this model for measuring items. And we're going to talk about measurement error. So what we do is we say that an individual measurement, so like one of these measurements when I measured my baby, the individual measurement is made up of the exact value, so my baby's true weight. If you had an incredibly precise scale, that would be the true weight. Plus some bias, which we'll talk about what bias is, plus some chance error. Okay, so the measurement error itself includes bias and chance error. So all the bias plus chance error, that's your measurement error. So you have your exact value plus some kind of error, gives you the actual measurement you get when you measure your baby's weight. So measurement error occurs a lot for repeated measurements when you measure the same thing over and over. But it occurs for more than that. It occurs for things like an observed value versus a true value. Or you say like your exam score versus how much you truly understand. Those two things might not be the same. So this is our model again. The measurement is the thing that you actually see. But there's a bunch of things that you don't see. So you don't see the exact value. You don't see the bias, and you don't know what the chance error is. So you don't know what those three things are. All you know is the actual measurement. So you don't know how it's broken down into the exact value, the bias, and the chance error. So let's talk about those three things. So bias is something in the measurement process that affects all the measurements in the same way, either by increasing all the measurements or decreasing all the measurements. So for example, 52, there's bias in the measurements when you weigh yourself with the same pair of shoes on every time. Because every time you weigh yourself, you're adding on the same amount of weight. So that would be an example of bias. Or another bias would be employees at a fabric store measure fabric with the same stretch tape measure every time. So if the tape measure stretched out an extra, say, inch, then they'd be adding on an inch every time they measure the fabric. Now let's talk about chance error, which is what we really care about in statistics. Chance error is a variation in the measurements that's just simply due to chance. So it doesn't affect all the measurements in the same way. So sometimes it might increase the measurement, sometimes it might decrease the measurement. And the source of the chance error isn't known. So for example, 19 students in a class were asked to measure the thickness of a tabletop using a vernier gauge that measures in 0.001 inch increments. So with it measuring in 0.00 inch increments, you think it would be pretty accurate. Each person made 2 measurements. They all measured the exact same table. So since they're all measuring the same table, you'd expect all their measurements to be exactly the same, or at least the 0.001 increments. But notice that they're really not. So the first person, he measured it once and got 1.317. The second time, he got 1.320. The second person got I think that's a typo, 1.326 and 1.325. The next person, 1.316 and 1.335, etc. So notice that every person is getting different results, and even like the same people, they're not getting the same results the first and second time they measure the table. So when person 1 measured the table twice, did he get the same result each time? No. Did any of the people get the same result when they measured it twice? So like if you look through any person, so person 11, 1.333 and 1.334. That's different. All of these people, they're getting different measurements when they measure it. And do the measurements vary from person to person? Yes. Obviously, the table's not changing width in between each measurement. It's just that we have difficulty measuring exactly. And we just chalk that up to the chance error. To estimate the exact value, we take the average of the measurements. The standard deviation of a series of repeated measurements estimates the chance error of a single measurement. Or in other words, the SD tells us how much we're likely to be off when we take a measurement. What do we do about measurement error? First, if there's bias, we remove it. If there's not bias, then the long-run average of repeated measurements should give the exact value of the thing we're measuring. Therefore, we do many measurements. So suppose a friend measured herself 4 times and got the measurements 135.98, 135.52, 136.1, and 136.4. The average of that list of numbers is 136, and the standard deviation is 0.316 pounds. So if she weighs herself again, she would expect to get, she'd expect to get the average, so 136. So she'd expect to get about 136 pounds, give or take 0.316 pounds or so. So again, the standard deviation tells you how much you're likely to be off. And repeated measurements usually follow a normal distribution, so about 95% of the time a new measurement will be within the true value plus or minus 2 standard deviations. Now outliers. Outliers are extreme measurements, usually measurements that fall more than 3 standard deviations from the average. Or you can think of them as outliers are measurements that don't seem to fit with the rest of the data. So for example 56, let's just look at the scatter plot and try and circle the data points that we think might be outliers. So I think this point and this point don't really seem to fit with the rest of the data. So I think they might be outliers. For example 57, circle the data points that we think might be outliers. I think that this point and this point might be outliers. What do we do with outliers? Outliers can only be discarded if our measurements have been taken incorrectly. So if we know that they're a mistake, we can take them out. But otherwise, if outliers are removed when they correspond to actual real data points, then the conclusions we draw from the data may be invalid. And so we don't want to remove them, we just have to deal with them, because we only remove outliers that were typos or mistakes. In summary, once again, your individual measurement is the exact value plus possible bias. There's not always bias, but sometimes there is, plus a chance error. To estimate the exact value, we take the average of the measurements. The SD of the measurements, the standard deviation, gives you the likely size of your chance error in any single measurement. And there's always chance error when you measure something, but there may or may not be bias.